Okay, all right. So
Reading next week.
here's what we're going to do. We're going to talk about Fourier transforms. And properties. That's what we're after. And first of all, let me put it on the board. If considering function f on negative infinity, positive infinity, as a Fourier transform, possibly, may have a Fourier transform, which would be f hat of omega, and that is the integral from minus infinity to plus infinity of f of x e to the minus 2 pi I omega x dx. Now, what's worth noting is that there's an inverse Fourier transform, a way to go backwards.
The formula we got last time didn't have the 2 pi in
Right, it probably had just the omega. That's right. So what I've scaled it appropriately. I've scaled it. So they're actually. This is important. There are several different conventions floating around for how you ought to scale them. The convention I'm going to use makes the next thing I'm going to write look prettiest.
it. Okay.
The convention that I wrote up last time is not quite as pretty in that regard. So the nice thing is you can invert this Fourier transform. I'll write up the other conventions as well. You can invert the Fourier transform. And the way you do it is a formula that looks almost identical to this one, except that there's the only difference really is a minus sign. That's why. That's why I picked the 2 pi in there. So, note other conventions exist. In particular, you might have one that looks like this. In which case the inverse Fourier transform has a different form. It's got an extra 1 over 2 pi in there. And I don't like remembering which one of these needs to have 1 over 2 pi in it. In fact, this is not the only other convention. There's another convention as well where you split the 1 over 2 pi between the two of them. You put square root of pi on each of them. You could do that as well. It makes the formulas the same, kind of like this. But take your pick. This one here is sort of the nicest. This is sort of the nicest one, so I think we'll go with that. Okay. So this is the Fourier transform. Now, what we had talked about last time was we had derived this Fourier transform from something. We derived it from what? We derived it from the spectrum of the Green's function, the spectrum of the operator, or spectrum of an operator looking at integrating its Green's functions. So let me really quickly recall what that is, because that turns out to be kind of useful. So, recall last time. What we did is we had something like this. We had an operator called L, and what L did is it took something from L2 and gave us another L2 function. And we supposed that we could write we knew a whole lot about its eigenfunctions. For its eigenfunctions. Okay, and eigenvalues. Okay. So we suppose that we knew those eigenfunctions and eigenvalues, or at least we suppose that these things define, perhaps in a better way to say. It's eigenfunctions and eigenvalues. Okay. And what we ended up doing was there was a little bit of power series magic that went into this, and we got some kind of formula. We said, suppose that we had some kind of formula like this for some function u. For some function u, I could write it in a Fourier series expansion in these eigenfunctions. And they went something like this. And this u is a function of x. This v is also a function of x. And of course, these are real numbers, and these are over all k's. So we suppose that we could write that. And what we did with this is we said, okay, this expansion is written out very nicely. Let's look at the situation, though, where perhaps we don't necessarily pick up all the eigenfunctions and eigenvalues in a nice way. Or perhaps we've got all these eigenvalues and eigenfunctions, but there's more stuff going on. So we looked at this, and this seemed a little unmotivated, and it still is kind of a little sophisticated. So we looked at this operator. This operator here does what for us? Well, it doesn't do a whole heck of a lot for us. This operator, though, if I try to solve an equation, like LU equals F or something like this, I can be in a situation where, let me make sure I do this right, actually I think I put LF equals U. LF is equal to U is I think actually what I'm interested in to make this derivation work. So we looked at this guy here, and we made the observation that F was L inverse of U. L minus lambda inverse of U. Now, the advantage or disadvantage of this situation is that, well, I don't know if this thing is invertible or not. If I suppose it is, I want to write this thing down in some kind of way that works out nicely with the fact that I know how to expand U. And here's the observation. The observation was that I could develop this thing here in a power series. So the tactic, again, this is develop a power series for L minus lambda inverse. And what that power series does for me is I'm able to write this thing out as something that looks like, well, what would be a power series representation? It would kind of look like, sort of notionally like, 1 over L minus lambda. And what I would imagine doing here is trying to come up with a power series in powers of L. Now, I don't know a power series for things like this, but I do know a power series if I take out a minus lambda out of the denominator, then I get something like this. 1 over 1 minus L over lambda. And how to expand that thing in a power series. 1 plus L over lambda plus L squared over lambda squared plus etc. The benefit of doing this is each of these guys here, each of these various operators, operates very nicely in this expansion for you. So notice, LU is what? It's L acting on this sum. And if I make use of linearity here, pull that L in, notice this is a scalar, so I can keep pulling until I get to phi k. And by definition of L of phi k, that's lambda times phi k. Now, if you look at this, you say, well, what if I did it again? What if I took another L and operated on this thing again? Well, I'd end up with a lambda squared where I've got the lambda. So in particular, lambda to the n up here, or L to the n there, turns into a lambda to the n. So in particular, if I develop a polynomial in L here and act on U, it ends up just turning into a polynomial in L on lambda k. So, well, what am I doing here? I've got this L minus lambda inverse, which is F acting on U, and that thing is then going to be sum of summing over k's, k equals 0 to infinity, of phi k u. And now here, I'm going to have just this L minus lambda inverse acting on phi k, which means that I'm going to get a polynomial. Now, this power series development, but what is this power series development? It's just 1 over L minus lambda. But now the L turns into the lambda k. Okay. So this was sort of the handy observation. And then what we said is, well, wait a minute here. If I take a look at this thing, I have some lambdas floating around here. Do I have any lambdas over here? No, not, well, yeah, I do, right there. Now, but I know how to write this guy down in a nice way. I know how to write this guy down in terms of a Green's function. This inversion operation here is really just having the Green's function act on U. That's what that whole process is. So this, if you will, is really just having the Green's function act on U. And this is, let's see here, I have not exposed any variables here. Let me expose a variable. Expose a variable. Variable Green's function of y d. Okay. So this here solves the equation L minus lambda f is equal to U. That's what this Green's function is. This g of x is the Green's function for L minus lambda with whatever boundary conditions are relevant. Remember, finding the Green's function involves finding the boundary conditions, or involves using the boundary conditions. Okay, now, at this point here, though, what have we got going on? Well, if you look at it, really what we have going on here is a situation where this g actually depends on lambda. So maybe I ought to sort of bump that in there and make it very clear that that's what I've got going on. G sub x, y, and let me put after the semicolon a lambda. Just to remind ourselves that that thing depends on lambda.
That should be lambda sub k, no?
And it is, no, it is just depending on lambda, not lambda
On the
sub
right
k.
side.
Oh, this should be sub k, yes, not superscript k. Absolutely, thank you. Otherwise, that would have been wicked wrong. Okay, right. Now, if I look over here, the lambda dependence of this formula is pretty easy. It just shows up right there. Here, the lambda dependence is kind of buried. Now, thus far, this has been a little crazy in that why would you do this? And the whole thing is set up so that what you can do is do a contour integral to make this thing turn out nice. And where we're going to contour integrate is along a circle of radius r. I'm going to contour integrate along a circle of radius r. Let's say it's oriented clockwise. It doesn't really matter too much. And so if I do that, I'm going to integrate both sides. This is dy, and now I'm integrating with respect to lambda. Now on this side here, I'm also integrating with respect to lambda over that same contour. But remember here on this side, the lambda dependence is only in one very narrowly localized spot, right there in that denominator. Everything else does not depend on lambda. So, in particular, what I really would want to do is sort of bring this integral all the way in here, pull everything else out away from the integral. Over here, I'll switch the order of integration here, so that that u pops out, and just buried inside is the integration with respect to lambda. So if I do that, make both of those transformations, I get integral uy, and integral, this one here, this outer integral is now the integral with respect to y. The inner integral is over CR, gx, y, and lambda, d lambda, y, and this whole thing is equal to sum, k equals 0 to infinity, of k u, k times this contour integral, d lambda over lambda k minus lambda. Now, this last integral right here, this one, what is that integral? Well, by the Cauchy integral formula, this function is analytic, or rather, not by the Cauchy integral formula, but this function is analytic for all lambdas except at lambda k. And so in particular, this is going to take on the value of 2 pi I, or 1 over 2 pi I, if and only if lambda k is in here, is in that circle. So this is equal to 1 over 2 pi I, if and only if lambda k is on the inside of that circle. So if the norm of lambda k is less than r. Exactly. So the right thing to do here, that's why I wrote the equals in the middle, is to take r to infinity. Then this thing is always equal to 1 over 2 pi I. Let's see. And I'll bring that in there. So I get something that looks like this. This integral times limit as r goes to infinity. R. This is equal to 1 over 2 pi I, or rather 2 pi I. Wait, is this equal to 1 over 2 pi I or 2 pi I? 2 pi I. Oh, where that 1 over came from. Alright, it's equal to 2 pi I. Okay, right. So this is equal to 2 pi I times this sum. Well, wait a minute, what is this sum? This is the Fourier series for u. So this is just u. So this is 2 pi I times u of x. Oh, well, wait a moment. And this was the punchline, the theoretical punchline. U of x is integral y 1 over 2 pi I, this limit, CR, g of x, y, lambda, d lambda, dy. And the moment you see this, you say, well, wait a moment here. For any such function u that this works out, this thing in here is working like a delta distribution. So the conclusion is, if it's going to be anything at all, it better be a delta distribution, because I can pick lots of different u's that I can write down to Fourier series representation. Now something magical happened. Something really magical happened. The thing that's magical is, what happened to the lambda k's? Where are they? Gone. Completely gone. They were just sort of a formal trick to get the right formula. So this notion that I had to write down this kind of expansion, this Fourier series expansion for u, was sort of a formal trick to get me to write down the right thing, get me to derive the right thing. So this allows me to write down this spectral representation of the delta function, which then looks like 1 over 2 pi I limit as r goes to infinity, r g sub x of y this is spectrum of the delta distribution. And then in particular, once you've got this in hand, then you can start thinking about what do you want to manipulate. The things you want to manipulate and the things that you want to study then are, this thing is telling me different ways to write these guys out. And by looking at these various Green's functions and looking at integration against them, splitting this up into various ways if you can, that's how you get different transforms. So, the Fourier transform comes from the case where L is two derivatives and there are no convolutions. Because then those eigenfunctions that you can write down are complex exponentials, for instance. Okay, and that delta function has got these sort of these two complex exponentials joined up in the middle, like we computed, I think, 2 classes ago. Okay, so that sort of brings us back to the main point of this, which is, all right, what are the various properties of the Fourier transform? And how are they useful in some sense? So what are relevant properties? Useful properties of well, so let's put that Fourier transform back on the board. Okay, so that's the Fourier transform. So let's see here. Well, first of all, this transform is pretty clearly linear in F. So the first thing is that it is linear. It's linear. Perhaps a different way to write this, to sort of emphasize this, you could write this as Fourier transform of little f, and we're going to evaluate it at omega. Different people write this different ways. Sometimes I like to write a script f here, and then maybe curly brackets, or whatever. I'm just going to use parentheses and straight letters to make it easier to write. So linearity, and the way that linearity works is if I AF plus G, that's A F of F plus B F of G. And that comes immediately from the fact that this is an integral. Because I just put in AF plus BG right in here, the A I pop it into 2 integrals, pull out the A, pull out the B. So that's end of proof for this. Now there's some more subtle properties that involve manipulating the integral structure. So there's some translation structure. So the translation property goes something like this. If instead I have my F, and I instead consider the question of what is the Fourier transform of f of x plus capital T. So what is it? Let's write it. What is T? T is some number, some real number. Some real number. Okay, so what do we do? Well, really there's only one way to address this problem, because I don't really know anything else about f except it's f. Like, that's it. That's all I know. So the only thing I really can do here is try to do a change of variables. So try to do something like y is equal to x plus t, and of course dy is dx. So what does that give me? Let's see, it doesn't change the limits because they're still infinity. So this is then f of y to the minus 2 pi I omega. But now here, what do I get?
Y minus 2.
Y minus t. Y. Now, notice this is an integral with respect to y. So the portion of this guy here, if I multiply this guy out, I'm going to get something that I can pull out. E to the 2 pi I omega capital T times this whole stuff. And that whole stuff is something we've seen before. That's the Fourier transform of y. So this is e to the 2 pi I omega tau, or omega capital T, times the Fourier transform. So if you scale, or rather not scale, if you shift time, translate time, it ends up scalar multiplying the Fourier transform. Now, when we look at the formulas for Fourier transform and inverse Fourier transform, which come about from the fact that put together they're going to give me these Green's functions, all that good stuff, what that means is that really translation ought to be dual to something else. There ought to be some other way to flip this around. And that brings us to what is called modulation. And essentially what this does, this says, well, we're going to shift the frequency. So what happens when we shift the frequency? So instead, we take, instead of omega, so given this guy, what is the inverse Fourier transform of plus, I need another letter. See? Should I choose a different Greek letter?
No.
No, you should choose different.
No. Leave it. Leave it.
All right, fine. Fine, I can see this is a heated topic. Okay.
It takes me like 3 seconds to repeat that one letter.
You get faster. Okay. So, what is the inverse Fourier transform of that? Well, let's just pop it into the formula. It'll take me 3 seconds to write that. I know what your problem is. And you say, well, wait a moment here. We just did this. We just did this a moment ago. Like, I can cut to the chase and just write this immediately out as e to the 2 pi I, e to the 2 pi cx, substituting the x's and x's as appropriate, times what? F of t. Now if you look at, f of x. If you look at this, what have we done? By shifting this Fourier transform, we've multiplied this by some kind of complex exponential that's time varying. This is some kind of sinusoid, if you will, multiplied by your original function. That's kind of interesting. Kind of useful, I suppose. Well, what else can you do? Well, you can scale. So instead of, and I always mess up the scaling, so I need to get that one right. Okay, here we go. The scaling law says we just take, instead, what is, it's going to be the same kind of proof, we're going to scale our time. Is f of x divided by a. Well, Fourier transform. Okay. Good notational convenience here is just to extend the hat over the whole thing. Okay, so what is that? Well, let's write it out.
Wait, why doesn't that, I'm a little confused as to why this isn't a linearity property.
It is not a linearity property because I am scaling f. F itself, the transform is linear in the functions,
Okay,
but I'm modifying the functions in a very different
Okay.
fashion here.
okay.
Yeah,